Okay, so hello everyone. Do you hear me? So today I would like to talk with you about a very cool, I hope you will find it cool, project. It's called the Fixed Gas Wasm. But before that, a bit of introduction. So I'm Yaron, I'm working for the project named Spacemesh. Spacemesh is a project that tries to implement a proof of space-time solution instead of the other popular alternatives like the proof of work or proof of stake. So Spacemesh is about proof of space-time, and also very nice and unique feature is that instead of having like a chain of transactions, the Spacemesh solution is about storing a thing. It's called a mesh. So each epoch that of a Spacemesh can have multiple miners. One second. Okay, now you can see this is the logo of Spacemesh, and this is the website. And I am the leader of the project called SVM. This is the GitHub of our project called SVM, and we use Wasm WebAssembly runtime. Basically, it's sorry. We use the Wasm project from the early days of Wasm, much before it hit the 1.0 milestone. And personally, I really like the company, and it's always very fun working with them. And the project, the father project, which is the full node implementation of Spacemesh, is called Go Spacemesh. So this is the link to the repository. As you can see from this prefix, it seems implemented in Golang, but SVM is a Rust project because it integrates with Wasm, and Wasm is written in Rust. So the way it works is basically we have some FFI layer that makes it possible to integrate with Go Spacemesh and SVM. A few words about myself. So I have started working on SVM, I think about 2 years ago, basically. SVM has gone through a couple of big changes over time, because as time passed, like requirements have changed, and we have refined things, and rewritten things. And right now it seems that the SVM is moving towards being stable and reaching some very mature phase. And a few recently, like I think 2 or 3 months ago, a very great person and developer named Filippo has joined me to work on the SVM, and we also have another position open for us developer in Spacemesh. And regardless, we have other positions that you can look at the website of Spacemesh. We are always looking for great people to join the project. So please take a look. Also, I'm very fond of the Rust programming language, and I love the Wasm, and I think it has a bright future inside the crypto scene, but also outside of it. I think that it can become like the de facto universal bytecode that we always hoped we will have. So it seems that it has a bright future in front of it. And this is a link to my personal website. And actually, it's very fresh. A few days ago, I've launched a new newsletter. So I will hope that you will find it useful. So please take a look, and maybe you will consider subscribing to it. And you can also reach me out over Twitter under this tag. It's called Real Wittenstein. So if you want to say hi or just follow me, so please. Okay, now please let's take a step back and forget for a second about the reason that we are here, and the fact that we are talking about blockchains and WebAssembly and crypto and all this stuff, and let's talk about something much more high level, which is life. Okay, so in life, as you know, life is one big trade-off. Everything is a trade-off. And software is no exception. Software also has a lot of trade-offs. And we need to find each time the right balance for us. So I've prepared this triangle containing three metrics, three, you could call it maybe vectors, that I think that it's very hard, not to say impossible, to fully reach entirely at the same time, simultaneously. So in the context of software, if we want to have a software that is very, very fast, super fast, and very, very flexible in terms of feature set, capabilities of the software, and also very, very easy to use from user experience angle, I would say that it's pretty much not possible to fully fulfill the three dimensions simultaneously. So if we want to have, for example, a software that is super flexible, contains almost a lot of very complicated features, and also very, very fast, it's fair to say that the user experience will probably suffer to some extent, okay? So this is when picking these 2 points. And let's take another example, another view. So if we want to have a software with a great user experience, and we want it to have a lot of features and being very flexible, it's likely that it will not be the fastest software that we could achieve otherwise. And the last case is that if we want to have a software that is very, very easy to use and super fast, we will probably have to introduce some restrictions, some constraints. So probably the feature that we will be able to implement will not be complete. We will probably have to decide to keep some of the features that we would like to aside, okay? And I would argue that basically in our scene of crypto, it's blockchain solution, it's very, very naive to think that we would like to be not the fastest as we can. We know how much it's important to have a good throughput, the number of transactions per a block, a layering, if we will use the Spacemesh terminology. So instead of looking at this triangle, I would argue that it's more like viewing these 2 metrics, okay? So we are left with creating a software or providing a solution that will be very flexible in terms of the features that we can implement on top of it, that we can provide, and we want also to have a very good user experience. So in Spacemesh, we want, the vision is that every person, even non-tech savvy person, like every person, can use our platform without being a programmer, without knowing what is WebAssembly and Rust, just being an ordinary computer user. Now, here we stand in front of a very, very critical decision, okay? It's either we pick the one or the other. I mean, we need to decide what's more important for us, okay? So let's stop the pause for a second and let's talk about the gas estimation problem. And it is actually like a direct continuation of the previous question that was asked during the talk. How do we estimate the gas cost for a transaction? So it all related to the halting problem. So Alan Turing, I think it was 1936, Alan Turing, or 1937, doesn't matter. Alan Turing proved that we cannot take a program, look statically or over the code and decide whether it will stop or not, okay? And this is something that each computer science student learns in the first lesson of the computability course. And this similarly naive or not very important proof is actually very, very dramatic to our world, because we cannot let someone just send a transaction, smart contract transaction that will execute on our platform without knowing in advance whether it will stop or not, right? So the solution that we currently pretty much have all over the place is to say, okay, I will do my best effort guess, and I will try to do whatever I can, learning from the history or performing some smart guesses, and I will do my best. And if the program will exceed this threshold number of steps, the gas units that I'm okay to allocate, then it will forcibly, we will make it out. We will enforce it to terminate, and the sender of the transaction will be like punished because the transaction will not reach its completion, but it still will have to compensate for this execution of transaction. So the gas estimation is something that we must deal with. We cannot escape it due to the halting problem. And this is really a good example of what we have just talked about being flexible and being easy to use. So if instead of calling it flexible and easy to use, we would say, okay, do we want to be Turing complete? When I'm saying Turing complete, I mean, do we want to support any kind of logic that we could possibly execute? Or do we more care about giving a very good gas estimation? Because if we want to be Turing complete, if we want to have no restrictions, basically, and we are willing to pay, for not having the greatest gas estimation, then it's fine. But in our case, in Spacemesh, for now, we have settled on moving towards the other side, and we put more emphasis of giving a very good gas estimation, a very good user experience, even though we know we will lose something. And it means that instead of being Turing complete, we will not be Turing complete. We are aware that we will not have everything, and we are okay with that. I mean, we might decide in the future to support another mode that we will support Turing completeness and using some not ideal user experience of gas estimation. But right now, and this is the focus of our today's talk, is that we are okay with adding constraints. We are okay with not being fully Turing complete, but we also want to accomplish a better user experience for the gas estimation. And this is the topic today. And this is what we have named the fixed gas, okay? And the fixed gas. So this is a background of the problem that we are facing, and now we will dive in deep how we went in with solving it. So we've got the SVM, which is basically using Wasm and extending it without functionality and adhering to the protocol of the Spacemesh full node. And this is fine, but we need to be able to produce some WebAssembly, and it's not really rational to expect people to write WebAssembly manually, right? So we need to have some platform to be able that will enable us to write smart contracts in our platform that will compile to a WebAssembly. And this WebAssembly, we want it to be compliant with the fixed gas Wasm. What it entails, I will expand not in this slide, but it's important to stress this. This is not just a general WebAssembly. It's not only a WebAssembly that needs to know how to talk with the SVM host. It's also a WebAssembly that will have restrictions that will enable us to give the fixed gas estimation, fixed gas, template. So in Spacemesh, we don't use the term smart contract. We use the term template. Template is a program, written, and the what's unique with having a template is that once you deploy a template to the mesh, yeah, which is like, we don't have a chain as a reminder, we call it on the mesh, but you get the idea. So once we deploy the template, we would like to be able to reuse it. Why? Because we don't want to find ourselves deploying the same code over and over again, which will bloat the mesh. So smart contract is basically named the template, and the way to develop a template right now is using the SVM SDK. It's like a Rust DSL. It is leveraging the Rust procedural macros. And if you will go to the GitHub, you can see a couple of SDK dash some word, and the primary crate is called SDK. It is the root one that assembles everything into one crate. And this code can also be compiled, of course, to Wasm. So this is how we are creating programs that can be deployed to the Spacemesh platform. Now, let's talk about the pipeline of the compilation, okay, a very high level. So we start with creating a program in Rust. We are using the Rust SVM, the SVM SDK, which is a Rust code, and it's using the procedural macros. And then the compiler expands this Rust code. And I've skipped here tons of stages that are internal to the Rust compiler. And at some stage, the compiler, after doing all its type checking and reducing the syntax tree and checking that everything is valid, like the borrow rules, and anything else related, we get to a point that we have some LLVM intermediate representation. And luckily, one of the backends of the LLVM is to Wasm. Now, again, we cannot allow ourselves to output any general Wasm because we want to deal with the halting problem, and we are okay with being non-Turing complete. So what we basically want is to reach the fixed gas Wasm, and the way to achieve it is to say, okay, in this stage, going from the SVM SDK to the expanded code after running the macros, procedural macros, in this transition, we have got 100% control, and it should be far easier to control things instead of from the Rust expanded code to the LLVM. So this is where we would like to tackle things. Now, let's talk about what we would like such a WebAssembly, what it means to have a fixed gas Wasm. What are the restrictions that we want this Wasm to have? So first of all, we cannot have loops, right? So we cannot have, for example, writing code in the Rust SDK. It cannot contain any for loops or while loops, cannot have any loops. The second one is also we cannot have a function calling itself, cannot have recursions, but we cannot also live with having a function A calling another function B and then calling another function C, which will call again function A, which started the call process, the call chain, because it means that we still introduced a loop to the program. Okay, so these three bullets basically means we cannot have any kind of loops. The last one says that we cannot have any polymorphism, because if we cannot assert in compile time what will be the target of the function being called, it means that if A calls, if we have some function A calling some B that we only know the signature of it, and then B calling another target having the same signature, it might be that B is calling itself, for example. So we cannot afford having polymorphism. So this is the high-level requirements for the fixed gas Wasm. Now let's talk about what it means in practice to have such a fixed gas Wasm. So if we don't want to have loops, the way to translate it into the Wasm world is to say we cannot afford having the loop opcode, okay? We just need to make sure that it will not exist. The second one and the third one basically translate that we need to make sure that the function cannot call itself for the cycle that I've explained. And the way to check that it's also by doing some validation, like validating that the loop opcode does not exist. And for polymorphism, also, we need to make sure that the call in direct opcode is not there. The SVM SDK emitted Wasm cannot contain these two opcodes. It cannot contain function calling itself, and it cannot contain any cycles, okay? So, a recap. We've talked about life, we've talked about software, we have decided that we are okay with not being fully Turing complete. We want to give a better gas estimation, which means a better user experience to the end user. It means that the contracts being deployed in our terminology of Spacemesh, it is the templates. We want the template being compiled to Wasm to be of a to be conforming to the fixed gas rules that I've outlined here. And now let's talk how to make sure that we can really achieve that, okay? So how can we really enforce the code of the compiler to adhere to these rules, okay? So, first of all, which is basically something that I guess any Rust programmer in the audience probably has already thought about. We will omit using the standard library of Rust. This is one of the strengths of Rust because it's super flexible. So even though Rust has a standard library shipping out of the box, we can decide that we don't want to use it. So this is such a use case. And the other one is that because we need to fill the gap into that was born by not having the standard library, is to come up with something of our own. So I've called it implementing a micro STD. So it means that since we cannot use, for example, a vector or of the standard library, or we cannot even use, surprisingly, the result type or the option type, we need to come with our own similar solutions that will eventually compile to the Wasm that we want. The third one is also very nice. I will expand on it I think it will be the next slide. It is the custom allocator. So similarly to the way that each program in Rust starts with a standard library imported in, and we can decide to discard it, to omit it. The same for the allocator. There is the default allocator of Rust, and we can swap it with our own implementation. And this is one of the very cool things that we are doing. And once we have got this free, it means we have full control over the allocations. We have full control over the STD because we are not using the STD. We are using our own crafted micro STD. What we are left with is doing iterations. We need to do a trial and error process. We write some code, we compile it to Wasm, right? The Wasm binary then is transformed into Wasm textual representation, which is Lispy-like, which is very, very handy. Then we inspect it into some text editor in the IDE. And if we stumble upon some piece of code that still is using, for example, a loop or the call indirect or a quotient or something like that, we need to think what we need to rewrite and how to close the gap until eventually, after a lot of iterations, we will reach a point that we know that the solution we've got is good for us. Okay, and it's not something that we can say we will, sorry, it's not something that is easy to know without doing this trial and error, because it's a lot of experimental work. It requires a lot of patience. And it means that each time in the future that we will have to, or we will need to add another feature of Rust to our templates implementation, it will be an opportunity to, or like there is a chance that we will have to come up with new solutions for that will extend the micro SSD. So it's this micro SSD involvement is it basically relies on what we will need in order to implement future templates. But even right now it contains pretty much a lot of functionality, but it's likely that things will change and that new types will be added. So a few examples. So in the micro SSD, we've got a vector implementation, which is not a resizable one, right? We cannot have any logic that we don't know ahead of time. So it means that when we allocate a vector, we know its capacity ahead of time. We have implementation that builds on top of this vector for a string, which again, we know ahead of time its maximum size, option types, results types, and a couple of others. And one of the disadvantages of this solution is that the output Wasm will be much bigger, because once you are not using loop, and we are using a lot of loop unrolling techniques in the code, which translate and compile them to a lot of repetitive code, is that, okay, the code of the Wasm will be bigger, but as I've explained here, templates for the rescue. So templates are a citizen in Spacemesh that is supposed to be relatively aware, like for each account in the system, for each template in the system, there will be tons of accounts spawned out of it, probably. So we get a lot of reuse. So it's, again, talking about the trade-offs, yeah. So in terms of code usage of on mesh, yeah, the template that we are compiling will be much bigger if we would otherwise just use loops. But really, it's not really an issue. Just saying that this is another example of a trade-off. So this is a very high-level overview of what it means to develop this SDK that will suit our needs. And now let's expand a bit about the custom allocator. So each time the program needs some heap memory, it needs to like do a knock on the door and ask in our case, it's the host of because we are running in Wasm in Sandbox. So it's like the operating system. It is asking for some amount of memory. We cannot use here, of course, malloc or anything that is that might contain loops and some significant computation. And the solution that we ended up with is that saying, okay, we know that we don't have loops. This is the assumption that we start with. And because we don't have loops, it's very easy for us to know ahead of time how much memory will be enough for us in any case. Okay, if you want another detailed explanation, I think it will be more obvious by the end of this talk, because I will talk about gas estimation in depth later. But basically, it means that we can reserve in one time the maximum amount of memory that we will ever need, thanks to the fact that we don't have loops. And it leaves us with doing a very, very simple allocation logic. It means that each time that a program is running, okay, this is the program in orange, and the purple is the WebAssembly runtime, the SVM. So each time the program needs some amount of memory, it knocks on the door of the host, okay, and the host will use the memory address of the instance, and it will just do an offset bump. It will increase the offset from old to new. And it will always take the same amount of time because it's only incrementation of a counter. So it means we can say that each allocation takes really the same amount of time, okay? We only need to take into account the fact that we once in the beginning, in the boot process, allocate one-time memory, and that's it. We don't care about how much we want in each future request. It will always be priced the same. So for those of you who might not know, there is some trait in Rust that you can implement your own custom allocator, and then you can call it the global allocator. And in the implementation of the alloc method of this trait, it basically just calls the host extern-C implementation, which when compiled to Wasm, it is transformed into calling an important function. And this and in the host, this counter incrementation takes place. Okay. Good. Okay. So the fixed gas validation and the pricing. So sorry. Okay. This is this chapter will talk about how we validate when given a WebAssembly program. Okay, we need to validate whether it is indeed a fixed gas Wasm. Otherwise, we need to discard it. And if it is valid, we need to know how to price it, the transaction, how to price each function. Okay, and these two share a lot of common logic because they are related. So again, we've got the SVM SDK. We follow the tricks, then the micro STD, custom allocator. We've done our experiments, the trial and error process, and we've got the Wasm. And now we want to validate it. Okay, a node in the network has received in its network from the network a transaction for please deploy me template, and now we need to assert whether it is valid or not. So what we are doing is we are scanning in one-time scan, linear scan of the call, and we are building while we are parsing the code a call graph. It means that each time that we are inside a function, let's call it a function A. Each time inside function A, we are seeing a call to another function, function B. And remember, we assume we are not using polymorphism. It means that we really know that FB, we know exactly what is the index of the function in Wasm. It's not that we treat it as something that we will defer only to the runtime, and it might be in theory a recursive call. We know what the FB is exactly in runtime by doing static analysis, okay? So we are building this call graph that each time inside function A calling a function B, we draw an edge between these two nodes. And while we are building the call graph as we go, if we for some reason encounter one of these opcodes which are not allowed, we halt the process and terminate and say that, okay, the validation fails. And later, once we've got the function call, the call graph, we need to look for loops, but not the loops opcode, but loops, the self loops like recursions and the call cycles. If you remember, A calling B, calling C, calling A, we don't want to have any loops. If we will find a loop in the graph, it will mean that the Wasm input is not a fixed Wasm, and it means that the validation fails again. So there is a very nice and easy and linear complexity algorithm called topological sort. And it means that if there is some order, might be more than one, but if there exists some order such that A is calling B, it's calling C, we will find it. Okay, and if for some reason the call graph contains a loop, we will find it as we go, and we will halt the process. And okay, so this is the validation of the fixed Wasm. And now comes I think the most fun part and the most interesting part is how to do the gas estimation. Okay, so again, we've got a Wasm, we have compiled it using our SDK. We have been good people, so we have deployed it. We have passed the validation, and we have deployed it on the mesh. Okay, again, on mesh, it's because we have a mesh and not a chain. And then now we are left with pricing. The lecture started with saying that we want to emphasize the user experience. We want to give some Bob before dispatching the transaction that if he will pay 10 units of gas, he for sure will be able to pay for its transaction. There will not be a case that the transaction will reach out of gas without terminating the logic, and then which means that Bob will be sad because he just got a penalty and no successful execution of transaction. This is the end game. Okay, this is the goal. We want to make Bob, which is not a tech-savvy person. He has nothing to do with crypto. He doesn't know what, for him, Rust is like a metal, okay? He doesn't care about blockchain. He just wants to get to use our application without knowing anything, like magic, transparently. Okay, so the way to be able to address this need of estimation goes like this. We've got a Wasm, and then we are using a technique that is commonly used inside the compilers world. It's called the control flow graph. In the control flow graph, each node in this graph is named the basic block, and it is a consecutive series of instructions that do not contain a jump. So in WebAssembly, we have a couple of jumps, couple of branching opcodes. It means that if we are starting to scan the code, as long as we are not reaching any branch instruction, we are good. The first time that we reach one, we need to close the node and create a new one and create an edge between these two, okay? So the control flow graph CFG edges represent the jumps, and I've also added something that I've named it continuations. You will see shortly, because I will present a couple of examples using real code. And it means that we can, by building this CFG graph, we can simulate any possible execution flow static in theory of the program. I mean, it's not exactly one-to-one mapping, because it might be that there are some paths that will never be able to execute in real life, but any possible execution could be also modeled using this CFG. Okay, so we are covered. And in Wasm, each function it's its own entity. So what we are doing is we build a control flow graph for each function, for each Wasm function, and we are pricing each function in isolation. Okay, now again, you can ask me what happens if function A is calling function B. How can you price both? So no, we are not doing it in parallel. We are doing it by the topological sort order that I've mentioned. If A is calling B, we will first estimate function B, and then only then we will estimate function A. And when we will reach the instruction inside function A that says call function B, by that point in time, we will know already what is the price of the function B. Okay, and because we don't have loops and we have a direct cyclic graph, it means that there is a solution and we can price each function. Okay, but before talking about the all program pricing, not only a function, let's focus on a couple of examples. Each example will show you a couple of lines of WebAssembly code in textual representation, and then we will see what this corresponding CFG looks like behind the scene. Okay, so this is the first example. This is the very, very simplest one. It's called we have here a function f0, with two statements, two instructions, asking for two local variables, okay, of the scope. So we will always have under the CFG of the current code, the start node. It is very handy technique to say that there will always exist node number 0, which is the start for everything. So there is no ingoing edge to node number 0, and it will be always an empty node. So this is why I have another edge of type continuation, which will take us to the second node with ID 1, and it will contain these two instructions. They both reside under the same node because these are not a branch instructions, so they need to go together, to sit together under the same physical node. Okay, so this was easy. Another one. So this example wants to deliver a point. In Wasm, we can introduce a lot of scopes by using the block keyword. So here we have got 3 nested blocks, but from the point of view of the CFG, we don't care. It's like saying we have got 1 block. Okay, so this nesting has no effect of the way we are building the CFG. Okay, now why it is important? I think it's important. I will give something that seems like a good example, because we don't want people to try to manually create some Wasms with tons of nesting, which will make our SVM work harder. Similar to the JIT bombs that people always mention, we are talking about compiling Wasm in smart contracts platform, and why they are using a single pass compiler. So this is very similar. So this algorithm of building the CFG is actually also linear. We can also do it in a single pass. I mean, this is the way it is implemented. If you are curious about the way it works, there is a crate called SVM Gaz under the project SVM. The name of the directory is just simply Gaz. And as you can see, it is single pass implementation algorithm. Okay, now the third example. This one contains a branch instruction. This is an unconditional branch. It means that each time that we reach this instruction, we will always jump to the right after this scope. So because this is 0, so it means that we need to finish this current block and move right here. So this line will never get to execute, never. Okay, so again, we've got here a block. We are executing the NOP operation in this, pushing to the stack this constant number. Then we jump right here, pushing the 30 constant number. So how it will look like? So we start again with the 0, and then we execute these two instructions. And because we are eating here a branch, we close this node and we create a new node, and we draw an edge of a jump. Now, as you can see, because as I've said, this instruction is unreachable, it means that in our CFG graph, this node will be unreachable, and later we will just ignore it or prune it when we will want to go to the next steps for doing the actual final estimation, the computation. But while building this, while implementing this algorithm, it's very handy to start with this implementation and just keep some unreachable nodes in place. Okay, so this is how it looks like. It means that once we are here, we always jump to this node, which is the final one. Now, this is the same example as number 3, but in this time, the conditional is, the branch is conditional, okay? It depends on the value fetched, the value of the top of the stack, okay? From what we've got at the top of the stack. So it means that we either break from the scope and again continue to the one instruction after the end of this block, this scope, or we continue to the next instruction. So let's see how the CFG corresponding one looks like. Again, number 0, we've got a continuation. This is the local get. And here we've got local get, and here we have got either we continue to the next one, or either we jump to the end. Okay, and as you can see, there is only one end node. Okay, always. So if the number 0 always exists and there's no incoming edges, the last one always exists and there's no outgoing edges. Okay. And now let's talk about if statements. Okay, so this is the if statement without an else block. It means that we only have if true clause. Let's see how it looks like. And here I'm drawing other types of edges that exist primarily for debugging and explanations, because there is no really any difference between having these two types of edges from the data structure perspective. It's mainly for us, the developers, to reason and to debug how things are happening. So if you will look at the code, you will see that I'm really using this terminology inside the code because it much eases the way to debug, like given some WebAssembly, what is the corresponding CFG looks like. So under this diagram, we've got continuation, we've got this statement, then we've got the if statement. If it is true, we are executing the NOP instruction, and then we proceed after the end of the on true block to the next. Or in this case, there is no really else, so we call it on if false because there is no else. So it seems like it seems like this. If the local get is true, then we are executing this NOP, and then after we are finished with the NOP, we jump right here. And if the local get is falsy, then again we jump again right here. So here this point is basically the same as saying number 3. Okay. So I hope that intuitively you understand. I hope that it seems intuitive and you get the idea in high level. And last example is again an if statement, but this time with an else block. If the if statement is true, we push 7 to the stack, otherwise we push 8. And after we are executing this instruction, we have to jump right after the if statement. Similarly, if it's falsy, we need to, to execute the else block, we need to execute this statement and then jump again to this point. So this point that both execute eventually, and this is the final node, is node number 0. Again, we start from number 4, sorry. So we start with 0. We push to the stack the local variable 0, and then we ask if the statement is true. We execute this statement and jump right after the end of the scope, which is in this case contains only a single instruction. If the if statement is falsy, we execute this instruction and then we jump over right after the else to the final one. So where we are means that given a WebAssembly, we can not only validate whether it's a fixed Wasm Wasm, we can also create for each function its corresponding control flow graph CFG. We know that the order matters because we need to be aware to the topological sort order. So we first start with nodes that so if A calls B, we first build the CFG for B and only then for A. And we've got only one part to discuss about. Okay, so how we take this control flow graph and how we can produce a number that will stand for the gas price. So what we are doing, and you will see a visualization right after this slide. So if you don't understand the text, that's also fine. Just try to be with me. Once we've got the CFG, remember, we've got the start node, which is always number 0, and we've got always the some end node, which its exact number depends on the code, but we know that we have exactly one such end node that we know that it is there. And between the start and end, we need to find the path that will give us the maximum weight. So each node inside the CFG will get some weight, some number. And after we will price each node, we will run an algorithm that will find the maximal weighted path. And this will be the number that we will use for our fixed gas. It means that no matter what our algorithm will run, no matter what, in what case, we will know that this max weighted path, which is the fixed gas, will be for sure enough for us. Now, we could take it one step further and say that, you know what, we've got the worst case. Let's signal the user that this is the worst case, and eventually implement something that will like use some gas metering, and then give him a refund back in the end. Right now, we are not doing that. Again, talking about trade-offs. The plus is that the person can say, okay, I will get a refund, but on the other end, you introduce gas metering, which also has some overhead. Okay, no, it's not only about running time. It's also about maintenance of a software. But we could do that. So what we've got right now is that once we've got the maximum path, this is the fixed gas, and this is what each transaction will pay for a given function. Okay, and how do we price a node? A node is a collection of instructions. If instruction contains a WebAssembly opcode or a call to the host, using the import function, each opcode will have a fixed price, and each import function will also have a fixed price. And this is the reason why our host functions of SVM currently are very basic, because we want to be able to give a fixed price to each import. And it plays nicely even with the allocation. If you remember that each allocation takes exactly the same amount of work, because it's only an offset bump. So even in that case, even for allocation, we've managed to find I think an elegant solution. And let's see how it looks like. So we've got here the table that for each opcode will give us its price. Some of the price are not relevant. For example, the if and else, there will be no if opcode inside the node. These opcodes are like if and else, and the branching, they change the way the CFG look like, the topography, the way the graph will look like, but there will be never any else opcode here or if or branch. Okay, so this is why there is a not available value here. And this is again the example number 6 that we've seen. No, sorry, it's a bit different. In number 6 we only had single statement. Never mind, but it's very similar. So if the if statement is true feed, then we execute. It's a bit tiny, but it's the const 7 and the NOP, and otherwise the const 8 and const 9. And here we've got a pricing for each opcode. So what we are doing, again, you see, I'm taking each node and I'm pricing it. Okay, it's very easy, just looping over the instructions and grabbing the associated opcode price by using this table. And once we've got this CFG with each node being priced, we need to find the maximum path. So in this case, there are only 2 paths, so it's very easy. It's very nice. One path is to say that we are going the left path, and the other one is to take the right path. And as you can see here, we pay 30, 20 plus 10, and here it's 20 plus 20. So the maximum weighted path is this one. Okay, so this is the winner. And 40 will be the price that we will pay for this function always. In order to find the maximum weighted path, it's also done in linear time. It's very easy to see why, because we have got here a DAG. It's similar a bit to the way we are doing the topological sorting. Again, you can view the code under the SVM repo, under the SVM gas crate, which is the gas folder. So we have got for each function its price. And so once we have got for each function its price, it means that when you execute a transaction, the transaction wants to call a function, we can give a price to the function. We need to take into account a couple of other variables, like the byte size of the transaction, the cost of allocating the memory once upfront when the instance of the Wasm is being booted, maybe a couple of other things. But in the end of the day, it's something that we can do very, very efficiently. And not only that, we can cache this logic. So, I mean, this CFG building its pricing for each function can be cached. There is no need to recompute it for each transaction, okay? Because we will always get the same result. It is agnostic to the state of the node. The other parts that are that might change between two transactions are maybe the bytes of the input or things like that. But again, it's just taking another variable and adding it to a counter, to a value that is cached. So it's very easy. Okay, so recap. We started the talk about the trade-offs, and as I've explained, in Spacemesh and in SVM in particular, we decided to put the emphasis on the fixed gas. We want to give the best user experience to the users that will use our system, our platform. The target audience is virtually every person that has a machine, not only very technical people. And once we have once we have taken this decision, the implied the side effects of it were that we need to be able to introduce constraints. It means that we will not stay Turing complete. It means that it's okay for us to not to support any kind of program. It means in very high level that we don't allow any sort of loops, no direct or indirect, no call cycles, no recursions, nothing. It means that there are things that we will not be able to support with this, but each program that can be modeled as a state machine without loops could be probably find a solution in our platform eventually. And even if it's not now, so probably in the future, as we continue adding more capabilities and features to the platform. And once we have taken the decision and we said, okay, this is the Wasm, this is the restrictions that we require from it, we need to specify what they are, and we have done it, and we've called it the fixed class gas, and then we've found a solution how to really make it practical and not only on the whiteboard. So we have a SVM SDK that we know that emits code in Wasm that is fixed gas. And once we've got fixed Wasm, we need to be able to first validate it. And if it is valid, then we need to be able to price each function. And this will be the value that will be used for the gas sent inside the transaction. The next steps, so this is a buzzword, we call it the smash lang. It means that we could decide to create something of our own, some programming language high-level one. It could be take something that exists like Solidity, for example, but only support a subset of it. For example, we cannot support loops, but support a subset of it. And there is also a third option that we can even think about some visualization, some application, some UI that will serve a lot of people in some very cool use cases, some applications, and the code of this application behind the scene will use, after being reduced to the SVM SDK, it will be compiled to this SDK Rust, and then transformed into the fixed gas Wasm. It means that we can see the SVM SDK Rust as the informal AST of our platform, from which we can infer we've got a solution for the fixed gas Wasm. So if we can take some AST and reduce it into the SVM SDK AST, then we are good. And yeah, and that's it, I think. Thank you. I hope you enjoyed it. Yeah, and that's it. If you have any questions, and you can also ping me later over email or Twitter, or yeah.